Hello, and welcome to today's webinar on rupture disks, sponsored by ZOOK. I'm Scott Jenkins, Senior Editor at Chemical Engineering Magazine, and the moderator for today's webinar, which is designed to help you select and size rupture disks, as well as troubleshoot the operation of your disks to ensure they perform optimally. Our speakers today are Rick King, Operations Manager for ZOOK Europe, and Peter Williamson, ZOOK Europe Sales Manager. Rick is a globally recognized rupture disk specialist and is responsible for developing and driving the operations of the ZOOK Europe, Middle East, Africa division. Peter has been in the rupture disk industry for over 25 years and has extensive industry experience in all aspects of rupture disk applications. He's played a key role in the establishment of ZOOK in the Europe, Middle East, and Africa regions, providing comprehensive pressure relief solutions for international ZOOK customers. Their presentation today will be about 45 minutes, and then after that we'll spend the balance of the hour in a question and answer session. On the left side of your screen, you should see an area where you can type and submit questions to the speakers. So feel free to send in questions at any time during the presentation. They'll be captured and saved. If we don't get to all the questions at the end of the webinar's allotted time, ZOOK staff will reach out to you and address your questions. If you experience any technical difficulties during the presentation, type a request for help into that same box on the left of your screen, and someone from the broadcast staff will assist you. I just want to remind everyone that the presentation will be archived for future viewing. So for a replay, you can either visit the chemical engineering website, which is www.chemengonline.com/webcast, and it will also be available under the resource section at zookdisk.com as well. I'll remind you of that at the end too. But at this point, I'm going to turn off and hand the program over to Rick and Peter. Go ahead, guys.
Thank you, Scott. Hello, everybody. My name is Peter Williamson, and I'm delighted to be one of your presenters today. Thank you for taking time out of your busy day to join us online.
Thank you, Peter. My name is Rick King. Some of you listening will know Peter or myself or both. Either way, I also want to thank each and every one of you who have taken the time to join us today. It's great to have you with us. Between Peter and myself, we have over 40 years of combined experience in the rupture disk industry, which is backed by countless more years throughout the ZOOK group. I can tell you that every day we're learning something new. This small, simple-looking device is actually more complicated than it looks. Our goal today is to try and share some of our knowledge and to help you understand some of the basics with these devices. We welcome your questions, which you can ask online at any time, as Scott mentioned. Before we start to discuss what you need to know about selection, sizing and troubleshooting, we want to provide a quick introduction to rupture disks. First off, what is a rupture disk? A rupture disk is primarily a safety device for pressure relief. Because of the very many ways pressure systems are designed and applied, the disks are also custom engineered to protect plant, personnel and equipment from unplanned or unexpected overpressure. In short, the disk is designed and specified to prevent plant from blowing up. It is generally a one-time use part using a calibrated thin diaphragm designed to rupture or burst at a designated pressure. What does a rupture disk actually do? A rupture disk is a differential pressure device. A proper rupture disk assembly creates an impermeable barrier in a pressurized system, and it bursts or opens when the differential in pressure across it reaches a designated level. We have a quick video to show you demonstrating a rupture disk opening. Let's play the video now.
Here you can see a rupture disk mounted to the end of a chamber, which is sealed at one end and a rupture disk mounted on the other. Pressure is introduced into the chamber and the disc bursts or opens when the pressure differential reaches the set point of the disc. Differential pressure simply means the pressure on one side of the disc is higher or lower than the other. If you pressurise both sides of the disc equally, nothing would actually happen. Here's another example using water. Rupture discs are custom designed safety devices. They can be engineered to function in both gas or liquid service, what we call compressible or incompressible service.
Okay, guys, I think you're clear to
No,
keep
we're
going.
good here, guys. Thank you. Compressed gas has far more stored energy than liquid, and the burst event is much more violent. In terms of rupture disc design, a gas burst poses significantly more challenges to rupture disc engineers. A simple way to explain what a rupture disc is and what it does is to understand that a rupture disc is to a pressurized system what a fuse is to an electrical system. It's a one-time use pressure relief safety device.
Rupture discs have been around for a long time and have earned an excellent reputation for successfully protecting all types of pressurized equipment. The original rupture disc was simply a piece of thin metal foil clamped between pipe flanges, designed to be the weak point in the system. As the internal pressure increases, the foil yields because it is thinner and therefore weaker than the vessel wall, eventually failing to safely relieve the overpressure and protect the integrity of the system. It was a simple design but very effective. The first design was patented in the early 1930s and is still produced by all manufacturers today. Later, 2 additional features were added to improve functionality. A reusable holder was introduced, improving burst reliability by holding the metal foil consistently and providing a better seal between both the disc and the holder and the flanges. The second improvement was to introduce pre-bulging of the disc foil to improve cycle resistance and reduce fatigue. The design is simple and fail-safe, relying on the tensile properties of the foil to control the bursting pressure. Since that first design, manufacturers worldwide have been working on new modern designs to address the demanding applications found in today's modern processors.
What are the advantages of rupture discs? Why use a rupture disc at all? Well, first and foremost, for safety and protection of personnel, plant, equipment and the environment. Pressure and pressurized systems are all around us, and an overpressure situation can be extremely dangerous. We just saw 2 very small volume-controlled demonstrations, but you can easily see the effects of the released energy in those small systems. Rupture discs are passive devices with no moving parts. Rupture discs provide leak-tight seals and are available in a wide variety of corrosion-resistant materials. Rupture discs are extremely fast-acting, typically going from closed to fully open in less than 3 milliseconds. Rupture discs are zero-maintenance devices with very high reliability. They are a time-tested safety product. Rupture discs are a very effective, low-cost solution to a pressure relief requirement. There is another method of pressure relief that most of you will be aware of, and that is a pressure relief valve, also known as a safety relief valve. A safety relief valve is typically a reclosing device, so why use a rupture disc instead of a relief valve? Let's look at cost. Comparatively speaking, rupture discs are very inexpensive compared to valves, which have large housings and intricate mechanicals, especially in larger sizes or when exotic materials of construction are required. Second is leak rate. Valves by their very nature can leak, which can be a problem in some services. Rupture discs, however, are virtually leak tight. They are basically a solid barrier with leak rates at the molecular level. The disc is very fast acting and, unlike a relief valve, does not require a change of direction for flow to take place. There are no moving parts in the disc, so reliability is high. There is no way to adjust the disc setting, which makes it tamper-proof. Notwithstanding the benefits of the disc, there are many cases where a relief valve is actually the preferred method of pressure relief, and we're the first to acknowledge this. The most common would be in processing or continuous service applications where downtime is a problem. A valve will typically reclose after relief, whereas a rupture disc would need to be replaced prior to a restart. There is a way to get the benefits of both the disc and the valve. This is a very common application where a rupture disc is used in series with a relief valve. In this case, the disc is placed immediately upstream of the valve, in essence isolating and protecting the valve from the process. The inexpensive rupture disc is the only part exposed to the process until an actual overpressure occurs. This is extremely advantageous in highly corrosive applications, combining the advantages of a fast-acting, leak-tight rupture disc below and the reclosing functionality of the valve above. Depending on the disc model, the valve can also be tested in situ without the need for removal, saving significant downtime and cost. There are, however, sizing-related challenges when combining the two types of pressure relief device that always need to be considered, and we will address them when we touch on sizing later on in the presentation. And because a rupture disc is a differential pressure relieving device, pressure cannot be allowed to develop in the space between combination devices, and a pressure gauge, tricock, free vent or suitable telltale indicator should be installed to ensure pressure buildup downstream of the disc is detected and eliminated. Rupture discs could also be used in parallel with the relief valves. A relatively small relief valve can handle any low pressure relief requirements, with a rupture disc to provide additional capacity for extreme requirements, for example a fire case scenario. This saves the high cost of installing a large relief valve, which is not required for most relief cases.
As you can see, there are many different designs to choose from, which can be intimidating for engineers trying to select the best design for their application. In an effort to simplify the selection process, we will build a family tree that groups similar designs. For this webinar, we are going to keep it simple and limit the discussion to widely manufactured designs and not custom hybrid designs. The first division is based on material, either metal or graphite. Metal designs are divided into forward-acting or reverse-acting. The common characteristic of a forward-acting disc is that the foil disc is made from and placed in tension when exposed to the system pressure. Burst is initiated when the tensile strength of the foil is overcome by the system pressure. For this reason, they are also known as tension-loaded. There are several designs of tension-loaded designs to allow better cycle resistance, burst control, or limit disc fragmentation. They are all still considered forward-acting discs. The common characteristic of a reverse-acting disc is that the disc foil is placed in compression when exposed to the system pressure. To do this, the foil is first factory pre-bulged into a dome shape and installed with the system pressure acting on the convex side of the dome. Burst is initiated when the disc dome strength is overcome by the system pressure and collapses to open along scores in the foil or by shearings or knife blades. These discs are also known as compression-loaded or reverse buckling. Again, there are several variations of reverse-acting designs available that enable us to select different models for increased available pressure ranges, tighter burst control, or compressible or incompressible service. Ultra-low pressure discs are also available, capable of opening pressures in the millibar range. It should be noted that compression loading of the disc allows the highest cycle life, with operating pressures of up to 95% of the disc's minimum rated burst pressure, without increasing fatigue or nuisance bursts. Extra care needs to be taken when selecting reverse-acting discs, as some designs are not fail-safe. Incorrect selection or installation can lead to dangerous situations. Reverse-acting discs can be more vulnerable to damage and are typically designed for either gas or liquid service. Graphite discs are made from naturally occurring black graphite that is simply machined into a rupture disc. The first thing to know about graphite is that in its raw state, it is essentially a black carbon sponge with approximately 13% porosity. To remove the porosity and create an impermeability, there are two processes undertaken by ZOOK. Resin impregnation is the first and most common process used. Various resins have been used over the years, but typically they are phenolic-based. Through a process that includes pressure, vacuum, and temperature curing cycles, the graphite pores are filled with cured resin that renders the graphite material impervious and suitable for use as a graphite rupture disc. Resin-impregnated graphite provides good corrosion resistance, inert material with non-ion contamination, temperature stability, and predictable results. Another process is a patented fluoropolymer sinter process. This involves preparing the graphite substrate to accept the fluoropolymer in a form both liquid and powder. The coated graphite is then sintered at high temperatures that produces a highly bonded coating to the raw graphite, resulting in an impervious material. In addition to all resin-impregnated graphite features, the fluoropolymer sintering process has greater corrosion resistance, allows higher operating temperatures, and holds FDA approval, and has a non-stick finish. As you can see, selecting the best possible rupture disc design is not a simple task for any one person to tackle on their own. Good collaboration between the end user, system designer, and disc manufacturer is essential in getting it right the first time. Every application has both common and unique criteria that will guide the selection process. Common criteria include the following: vessel maximum allowable working pressure, otherwise known as MAWP, disc burst pressure and temperature, normal system operating pressure, operating ratio, burst tolerance.
I want to take a minute to point out that we often do product training and factory schools for clients, channel partners and employees, and this section of the training normally takes 4 to 6 hours. We could easily spend an entire day going over industry definitions, rupture disc terms and models, and the methodology for selecting rupture discs. For the purposes of this presentation, we will only be reviewing the key parameters. It's also worth mentioning that this webinar is aimed at European style specifications relating to the Pressure Equipment Directive and EN ISO 41262. Our last webinar talked about the North American ASME style specifications based on manufacturing range. That webinar is available online, or if you have immediate questions, please enter these online. Maximum allowable working pressure is defined as the pressure limit of a vessel as determined by the manufacturer. Any pressurized system that a rupture disc will be protecting should be rated with an MAWP. A rupture disc chosen as the primary relieving device should not have a burst pressure greater than the vessel MAWP. Choosing a burst pressure below, even well below the MAWP is fine, but above is not. As such, the MAWP forms a basis in the pressure setting and sizing for the rupture disc. It should be noted that choosing a rupture pressure lower than the MAWP will result in a larger size during sizing calculations. Specified burst pressure is defined as the desired burst pressure of the disc as supplied by the end user. Simply stated, this is the value as specified by the end user as the pressure at which the disc should burst. Typically, a process engineer will determine the specified burst pressure in their overall system design calculations. This is the critical value provided to the disc manufacturer. System operating pressure is the normal operating pressure range the disc will see in service. The disc maker needs to know this to be able to choose the correct disc model. For example, some basic discs cannot tolerate operating pressures close to the rated burst pressure. Other designs may require extra components to withstand vacuum conditions. Now considering operating ratio. We just talked about the importance of knowing the operating pressure range for the process so that we can choose the right disc design. Different discs have different ability to withstand high operating pressures. The operating ratio is a measure of how close the operating pressure is allowed to be in relation to the burst pressure. The higher the disc operating ratio, the better that disc design will be able to tolerate a high operating pressure. Burst tolerance is the allowable deviation from the nominal burst pressure of the disc. All rupture discs are specified with a tolerance. The disc is completely dependent on the absolute properties of the material of manufacture, which are inevitably subject to variability. This is reflected in the burst tolerance, which allows for this variability. Tolerances can be made tighter. There are extra testing costs for the maker, so a tighter tolerance is reflected in a higher disc cost. This slide shows how the different tolerances are specified in the European format. We can have a nominal rating with tolerance, or state this as a minimum and maximum. What this gives the user is a fully transparent indication of the expected disk performance. On the left chart, we have a standard tolerance disk with tolerance plus minus 10%. If the process demands a tighter tolerance, we can go to the right-hand chart, where we have the same nominal rating but a tighter tolerance. What are the benefits of the tighter tolerance?
We can see that here. With any disk, we will always have the red band sitting below the burst rating of the disk. This is the area where the disk should not be operated in normal service. If the operating pressure heads into this area, then the disk should not burst immediately, but it will be fatigued, leading to a low or nuisance burst. If we tighten the tolerance, this can allow the operating pressure to be higher without stressing the disk. So let's see how this all fits together. This slide is an example of a simple decision tree that goes through the decisions you must make and the information you need to have to select the correct rupture disk for your new application. I emphasize new because the process is slightly different when troubleshooting an existing application. The first step is to gather all the information you can, both general and specific to your application. Next, you need to get your calculator out and work out the operating ratio required for the application. At this point, you can start to filter out some designs based on the general information you gathered and calculated in previous steps. It is really a process of elimination. Operating ratio eliminates designs that cannot handle the calculated operating pressure. Fragmentation eliminates designs that don't meet the fragmentation requirements. You should now have a short list of potential designs. At this point, you need to look at more specific attributes to your application and decide on how they affect your shortlist designs, and again eliminate the ones that don't comply for one reason or another. Some of the considerations are: is the process medium, liquid or gas? Eliminate designs that are not suitable for the specified medium. Burst pressure. Eliminate designs that are not available at the desired burst pressure. Size. Eliminate disks that are not available in the specified size. Burst temperature. Eliminate designs that are not serviceable at that desired burst temperature. One last check to make sure you have not overlooked anything, and you are done.
As a maker, we are not asking the user or even the specifying engineer to make disk selections. This is where we can help you. The earlier on in the design stage you can involve the disk manufacturer or their channel, the better. Only a collaborative disk selection process will result in finding the best disk for the application.
Rupture disk devices are accepted by various national and international codes as a means of protecting a pressure vessel against overpressure. These codes all provide guidance on generally accepted formulas and approaches. Proper sizing of a rupture disk device is as critical as selecting a proper disk design. Undersizing will allow the pressure to rise to an unsafe level because the pressure is being generated more quickly than it can be vented. Oversizing is equally dangerous because the device may not open as intended, limiting the device's relieving capacity. This is particularly true with reverse acting disks that require minimum amounts of burst energy to open the disk as designed. There are two recognized sizing methods. The first, known as coefficient of discharge, and employs a fixed value known as KD to calculate the theoretical flow rate for a given disk size. This method is also referred to as simple sizing and can be used when the inlet and outlet piping are at least the same size as the rupture disk device. The device is located within 8 pipe diameters of the vessel connection. There are less than 5 pipe diameters of outlet piping, and the device discharges directly to the atmospheres. ZOOK offers a web-based sizing tool to assist with simple coefficient of discharge sizing. We're going to play a video now to demonstrate some of the features of Z-size.
What you see now is the sizing project. The project is designed to contain one or many individual sizing calculations. The project ID is assigned by the program once I've clicked on Save, and I've also filled in fields to show the project name, customer reference, the project date, and some notes. By clicking here where it says Sizing 1, I can begin the first sizing within the project. I'll start by filling in the tag number field by typing in a PSE number. Notice that here on the side, you can now see your tag number referenced. The revision number field can also be filled in with whatever reference you would like, and its entry will append to the tag number displayed on the left. Next, we have a choice to solve for either MNFA or capacity. MNFA stands for minimum net flow area. If you choose MNFA, you can enter the capacity values, and the calculator will show an MNFA result. If you choose capacity, you will enter the MNFA value, and the calculator will show a capacity result. For this example, we'll solve for MNFA. Sizing code is the next line, and the Z-size offers 3 calculation standards: API, ASME, or ISO. While the required information is very similar, the 3 codes do use slightly different formulas for their calculations, which we will see displayed later in the printout. Next, we can choose the fluid state. The 3 options are gas, vapor, liquid, or steam. The combination of sizing code and fluid state will determine which of the standard formulas Z-size will use in its calculations. All of the calculations in Z-size are based on a sizing method using coefficient of discharge, also referred to as KD. The next line has fields for purpose and relieving case, and the combination of these choices will set the overpressure allowance on the next line. The next line is where we will enter the required capacity. There are several units of measure to choose from depending on the fluid state, gas, steam, or liquid. In this example, I'll use 25,000 pounds per hour. Next, I can enter the burst pressure, which is the set burst pressure of the rupture disc. Clicking here where it says PSIG, you can see there are several choices for pressure units. For this case, let's use 100 PSIG. Here's where we can enter the burst temperature. This should represent the temperature in combination with the burst pressure at which the rupture disc should be expected to burst. Now we can look at the fluid properties. Since we've selected gas as our fluid state, we have a selection of several common gases. Choosing a medium will also show the corresponding values of that particular gas for ratio of specific heats, molecular weight, specific gravity, and density. Now on the right side, we can see the results of the sizing calculation. Since we're solving for MNFA in this example, Z-size has calculated the required MNFA is 3.876 square inches based on all of our information entered in the left pane. In the unit of measure dropdown, you can also choose centimeter squared or millimeter squared. Here, by equivalent diameter, the calculation is simply converting the MNFA in area to its equivalent diameter. In this section called Enter Disk Specs If Known, we are giving you the opportunity to enter the MNFA of your own rupture disk, and Z-size will calculate the resulting capacity. Calculation is using all the information that's been entered on the left side. So if I enter 5 inches squared, the calculation result is 32,247 pounds per hour. Here again we have the drop-down fields that give some flexibility to enter different units of measure. Next, I'll show you how to add, copy, or delete individual sizing within a project. Over here on the left at the top, you'll see 2 icons. The first is a plus sign that simply adds another sizing to the project, and the second icon is for copying a sizing. If I click on the copy icon, we now have a line that is an exact copy of the first one. Here we can change any of the fields to evaluate the impact on the size calculation. For example, I'll change 25,000 pounds per hour to 30,000 pounds per hour, and the resulting MNFA changes from 3.876 to 4.652. Here at the right top corner of the screen, you'll see icons for print, save, save and exit, or exit without saving. If I click on print, Z-size will generate a calculation sheet with the information from your sizing entries and the results. It will open on a separate tab in your browser, and from there you can select your print options. Now I'll click Save and Exit, and that will bring us back to the main screen. Here we can see that your sizing project has been saved to the database. At this point, if you're finished, you can log off or simply close your browser, and your sizing project will be saved for the next time you log in. Thanks for watching the video on Z-size. Please contact ZOOK if you have any questions regarding Z-size or your rupture disk application.
Z-size is a great tool that can be accessed by anybody from a link on our website. Please give it a try. Our second sizing method is resistance to flow and differs from coefficient of discharge because it considers all piping components in the relief system. The KR value of each component is added to develop a total K value for the system. The system K is then used to calculate the capacity of the entire relief system. Sounds simple, but a complete knowledge of the full relief system is a must. Typically, this method is used when the coefficient of discharge method does not apply. Caution should be taken when selecting rupture disc designs based solely on low KR, as this can lead to a small diameter relief system with limited options to correct the situation if changes in the disc or pipework design are required in the future. Vendors can offer useful advice and sizing assistance, but ultimately, it's the responsibility of the sizing that lies with the end user. The takeaway here is that right sizing is the goal, which requires collaboration between the user, process engineer, and disc manufacturer. Rick mentioned earlier an application that includes a rupture disc device in combination or in series with a pressure relief valve. For this application, the sizing is based on the pressure relief valve capacity. The effect of the upstream rupture disc device is accounted for by applying a default of 0.9 capacity factor, or CCF, to the valve flow capacity to give a conservative relieving capacity for the combination. A certified CCF for the specific disc and valve combination can be derived by actually flow testing. This will typically give the higher CCF, meaning a lesser derating of the combination. Caution is advised not to rely on the high certified CCF value. Doing so will limit flexibility if changes of the rupture disc or pressure relief valve are required in the future.
It's important to remember that a rupture disc is a device that is designed to burst. Some people say designed to fail. We like to say designed to burst or activate at a specified point. Just like any other engineered mechanical device, things can happen to affect performance, and this is when disc manufacturers have to use some detective work. First and foremost, rupture discs will not last forever. They are mechanical devices exposed to various forces, temperatures, and other process conditions, and therefore they can fatigue. So bursting low may simply be a case of continued exposure to demanding service conditions. Why do rupture discs fatigue? The reason is that by design there is no way to build in extra strength to allow the disc to allow for corrosion and loading. This is at the same time both a blessing and a curse, as the lack of over-design, what would normally be considered a safety factor, is at the heart of the rupture disc function. It is also what will give the disc a limited service life if the service conditions are demanding. This is why the disc maker should be your partner in evaluating the process and selecting the right disc from the start. Rupture discs are engineered products, but they can be delicate and fragile. Especially with reverse acting discs, any minor damage to the disc dome will negatively affect performance and cause the disc to burst or collapse low. All disc manufacturers will take extreme care to fabricate, package, and ship you their discs in good condition, but handling in the field is just as critical. Discs should always be handled by their edges or tags. Never touch the disc dome. If a disc shows any signs of damage whatsoever, it should not be installed. Consult the maker. Disc damage in the field is the single largest cause of nuisance bursts. I use the term nuisance burst loosely, and what I mean is a burst at a lower level than specified or expected. Nuisance bursts are expensive and result in significant loss of product or time or both, so they need to be avoided. We had a situation a while ago whereby a client contacted us because they were having performance problems with a competitor's product. Namely, they were experiencing nuisance bursts. Adding to the base problem was that their equipment was very remote and unmanned. Every time they had a burst event, they had to send a crew out for an expensive repair. They simply thought there was an issue with the disc design and performance. It turned out that in order to reduce cost, the inlet side of the holder had been reduced to a point where the disc dome protruded beyond the holder face, similar to the assembly on the left. This can create problems during installation, as it is easy for the dome to be impacted during handling and insertion of the assembly between flanges. This can go undetected until it results in a service issue, and this is what was happening. Our solution, on the right, was to simply provide an assembly with a similar disc style with a pre-torque holder that sealed the disc and fully protected the dome. Problem solved. It's important to realise that a rupture disc assembly is typically another joint or connection point in a pressurised system. All rupture disc manufacturers have recommended bolt torque levels for their designs, and following these recommendations is critical to achieve a leak-tight connection. Some disc designs are extremely torque sensitive, and over or under torque can cause disc damage or leakage. Most rupture disc assemblies utilise gaskets to seal the device into the piping, so gasket style and more importantly gasket integrity is critical in ensuring a proper seal. The disc itself is normally sealed in the holder using a metal-to-metal seal, so it does not need a gasket within the holder. Misaligning holder and disc components or incorrect torque patterns can also cause leaks. Similar to any tightening process, it's important to gradually increase the torque around the flange in order to provide equal loading to the assembly. Misaligned piping like that shown in this picture or incorrect flange torque can result in multiple leak locations across a rupture disc assembly. Some manufacturers offer pre-torque holders which allow the installer to preload the disc and create a leak-tight assembly prior to field installation. There are various methods used to seal the rupture disc within the assembly. This varies from manufacturer but can include O-rings, pinch points, welds and metal bite rings. Care should always be taken when handling holder sealing surfaces and they should be inspected every time a disc is changed. Any damage to a sealing surface can cause leaks. In this picture you can see that the raised sealing bite section of the holder has been damaged, which could create a leak path in the assembly. Not all holders or disc assemblies are suitable for every situation. If you are having a leakage problem and you're confident that your discs and holder sealing surfaces are not damaged and that you are following proper installation procedures, then you should contact your disc manufacturer for help. If you do have a problem, we want to help you. How can you help us? Get the lot number of the affected disc or discs. All manufacturers use lot numbers to identify manufacturing batches of the product. This number gives us access to every aspect of the disc's manufacturing history and is critical for investigative work. What else? Have the installation history at hand. Is this a new or existing installation? How long has the disc been installed? Have any of the process conditions changed? Have problems begun with the recent shipment of product? Take plenty of pictures, the disc, holder, flange setup, upstream and downstream. All this information builds a picture in diagnosing problems and finding engineering solutions. And then contact the factory. This can be done through your manufacturer's local channel partner or whichever is the normal method of contact for you, but ultimately your issue will make its way back to the factory for analysis. All disc manufacturers will have a quality and technical support team available to help you. They will all take performance issues with their respective products seriously. We're all in the business of making safety products, and we take that responsibility very seriously. Do understand that remotely analysing or forensically diagnosing performance problems is difficult for disc manufacturers to do alone. We need your help. It's rarely the disc's fault. It's a mechanical device simply reacting to its environment, and it's up to all of us to work out the best engineered solution when a problem arises.
People ask us all the time, how long will my rupture disc last? The truth is nobody knows, and scheduled preventative maintenance is recommended. Or if the process is down, take the opportunity to change out the disc. In absence of actual installation history, we suggest starting with a 1-year interval between scheduled disc replacements. We understand how self-serving this sounds, but it is better to have a proactive preventative maintenance. The cost of replacing a disc is far less than the cost of unplanned shutdown and the resulting loss of product and production. There are no specific maintenance tasks that can be performed on the rupture disc. If a metal rupture disc device is taken out of service, then it should be replaced, unless it is assembled into a pre-torqued holder. Pre-torque holders with integral pre-torque bolts can be removed from service, inspected and reinstalled safely because the seal between the disc and holder is not disturbed. Holderless graphite discs can also be reinstalled after inspection. During disc replacement, personnel can perform maintenance tasks on the rupture disc holders. First, the holder's gasket surfaces should be examined for foreign material. Any adhered gasket material from the previous installation should be cleaned from the gasket surfaces of the holder thoroughly. Dirt and grit on these surfaces can also cause leaks. Next, the seat area should be inspected for scratches, dents or nicks because imperfection in these surfaces can also cause leaks. Care should be taken not to introduce any new scratches into the sealing surface. A clean cloth with a suitable solvent can be used to remove residue. If that does not fully remove it, fine emery cloth or steel wool can also be used with caution, not to damage the surface by pressing too hard and making grooves or scratches into the sealing surfaces. If scratches, dents or nicks are present, contact the manufacturer. Never machine or modify the holder. The geometry is critical to the disc performance. In summary, prevention is always better than cure. Be ahead of the game and keep your process team happy and your people safe by being proactive with the defined maintenance and change-out regime. In closing, all rupture manufacturers offer good quality products that will work as intended, provided they are selected, installed, and applied correctly. We need your help to ensure this all happens. Thank you for listening.
I also want to thank all of you for your time today. I hope we've managed to increase your understanding of rupture discs, and to echo what Peter's mentioned, a collaborative effort between yourself and your rupture disc manufacturer will ensure a proper sized and engineered solution for your pressure relief requirements. Thanks again.
All right, great. Thanks, guys. This is Scott Jenkins again with Chemical Engineering. We're going to get right to some questions for Rick and Peter. So the first question is, can you please comment on how process temperature variation is taken into account in selecting the burst pressure and fabrication of the rupture disc?
Well, Scott, firstly, thanks for the question. It's a good one. Disc performance or the rating will vary with temperature. That's because the material strength changes with temperature, and we're talking about the absolute properties of the material here. So if the strength of the material shifts a little bit with temperature, then the burst pressure changes at the same time. We can look at different materials to mitigate this. Graphite discs are temperature stable. Inconel and nickel are relatively temperature stable if we're looking at metal discs. The upshot of this is that if we have a disc rated at room temperature and we work it at a higher temperature, maybe 100 degrees, 200 degrees, then it's going to burst lower than it would at ambient temperature. So if there are variations in the process temperature, the process engineer needs to look at what temperature the disc will see on burst. You might have a process that's largely at ambient temperature, maybe at low pressure, and the disc is there to protect during a cleaning in situ process, steam cleaning for example, and in that scenario the disc will burst when it's seeing a high temperature. So in that case the disc should be rated at the temperature of the steam in that process. If in doubt, the safest thing to do is rate the disc at the lowest temperature it's going to see in operation. That means it's going to burst safe, lower, if it does see the higher temperature. In terms of testing, best practice and our policy is to test discs at the rated temperature. That ensures that the disc will work as the specifying engineer expects. Thank you, Scott.
All right. Yeah, that sounds good. The next question is, do all rupture discs require a holder?
No, Scott, not all discs require a holder. We do have some designs that fit directly between flanges. These types are normally for low pressure applications. For higher burst pressures and for high performance discs, a disc holder is the better option. Using a disc holder ensures the geometry around the disc is well controlled. The disc holder is also there to protect the disc during installation.
That's a good answer, Pete.
Right.
Scott, what do you have?
Yeah, thank you for that. That's good. So let's move on to the next one. You mentioned in the presentation that caution should be taken when using KR as a sizing basis. Can you explain this further?
Yeah, I'll take that, Scott. Rick again. Fairly deep question. Thank you for that. Yeah, the K system is a good method of sizing, no question about that. And what it is a whole system analysis. So what the process engineer is doing, or the pipework engineer is doing, is looking at every part within the system, They're taking a value for each part, which represents the resistance to flow of that component, and they get added together to make an overall K value for the system. And the bottom line is, the lower the K number that you get from that sum, the better the system will flow. So if we look at a disk, typical KR values for ZOOK, we're starting at about 0.26, and most disks are in the low single figures for the KR value. If you look at an overall system figure, those numbers are more likely to be into double figures. So that disk value is a relatively small part of that overall sum. So what does that mean? What it means is that if you halve the disk KR value, you're not going to double the capacity of the system. It's just a small part of the overall picture of the entire system. Either way, if you're doing that K evaluation for the whole system capacity, makes good sense to allow a bit of leeway. Legislation changes, processes change, which means you may need a higher flow capacity. So if you're designing right to the margins of flow capacity by looking for the very lowest K values, if you need to do a modification later, you may find yourself boxed in. So that's why we'd recommend going for a little bit of margin there, just to allow yourself something.
Okay.
That's all I have on that.
All right, that's so yeah, the next question is for lined disks, do the burst tests include the liner?
Scott, we always test representative samples of discs ordered by the customer. So if the disc is ordered with a Teflon liner, the burst testing of the disc is done with the Teflon liner in place. The same applies for any other accessory parts which have a potential to affect the disc opening, for example, an integral burst indicator.
Yeah, I'd add to that. What we're trying to do, as Peter just said, every time we do a test, we're always trying to make sure that what we're testing is what the customer will receive. So the results we get are completely representative when the disc is put into the installation.
Yeah, that makes sense, definitely. So let's go to the next one. So the next question is, what is vacuum support for a rupture disk, and how does it work?
Okay, Scott, Rick again. I'll take that. It's a common condition, common question. Lots of processors have vacuum as part of the process, and in most cases the disk needs to withstand that vacuum. The disk's a differential pressure device, and all that vacuum represents to the disk is a reverse pressure differential. It's pressure in the opposite direction to what it normally experiences. A lot of disks, especially modern designs, will handle vacuum by design, so you don't need any extra parts. Reverse acting disks in particular are resistant to vacuum and even back pressure as well, so that's higher reverse pressure than a vacuum can create. If the disk design can't cope with vacuum, but there's vacuum in the process, then what we can do is put a vacuum support generally immediately below the disk membrane, and that can be the graphite membrane or the metal membrane. That vacuum support is going to closely follow the profile of the disk membrane, and that will support it when you get that reverse pressure. So what that means is, in many cases, that vacuum support actually stays in place once the disk has burst. And that means, in turn, you're going to get a reduced flow area when the disk opens. And because you've got some more complex geometry layout around the flow, the disk KR value may be pushed up as well. Some designs of vacuum support open with the disk. Even then, you're likely to get some reduction of flow and some increase in KR number. That's why modern designs have been developed, because the makers, responding to the needs of the market, we're trying to get away from disks that require vacuum supports, but sometimes it's either the most economic way to get the disk in place, or it's the only solution for the design we need to install.
All right, thanks for that.
Thanks, Scott.
All right, moving on to the next one. So the question is, how close is the burst pressure to the set pressure of the relief valve? if it's installed in front of it. So if the disc is installed in front of it.
Okay, Scott. Yeah, for a disc set in series with a safety relief valve, typically the disc will be set at the same pressure as the safety relief valve it is protecting. If the disc is set at a lower pressure, there is a possibility that the disc could open, but the valve will remain closed, resulting in the safety relief valve being exposed to the process conditions which the disc was there to shield it from. Normally, there would be no reason to rate the disc above the valve rating. If the disc is installed as a secondary relief device, the burst pressure of the disc will be set above that of the safety relief valve. The valve will deal with any low-level pressure excursions. The function of the rupture disc is to be the final fail-safe device in case the valve does not function correctly or cannot relieve the system flow quick enough.
All right. Let's go to the next one here. So the next question is, do you make a rupture disc that ruptures at low pressures, for example, say 20 millibar G?
Scott, I'll take that. Thank you. Rick again. The quick answer, yes, we do. There are some big challenges there because if we think about 20 millibars, that's pressures in the inches of water column range. There's very little energy there, but we need to use that energy to make the disc open. So we're trying to break something using very small amounts of energy. So there's a few ways we can do that. One is to go for a very large disc. So that big active area gives us lots of, allows us to use even that low pressure to generate enough force to actually break the disc, whatever the seal or membrane material is. More practically, because generally we don't want to be installing huge discs where the flow requirements don't merit that, is to go for a development of a reverse acting discs. And when we do that, what we're doing is taking the two elements of the disc function, that's the sealing function before the disc opens, and then the opening function or the response to pressure, and we're separating those. So for sealing, we're using a Teflon film, and we're using that to seal the disc. To control the opening pressure, so to get the response at low pressure, we're taking a reverse acting disc dome, and we're actually cutting that away. We don't need it to seal because we have the Teflon film, so we're cutting that away. The seal bears onto that cutaway disc, and when we reach the collapsing pressure of that girdle, as we call it, then the disc reverses. At that point, the Teflon film is opened, and that's done by a cutting blade or a knife blade assembly. A lot of people may be looking at that and saying, well, knife blade assemblies are not good. Generally, that's good. The very original designs of reverse acting discs were using knife blade assemblies. The difference here is that they were required to cut a metal disc, a full metal disc. For our low pressure disc, we're just requiring the blades to cut the Teflon seal, and that's a very, very different requirement for the holder. So to sum up, yes, discs in the 20 millibar, lower or higher ranges are definitely attainable.
Okay, great. That's helpful. So next question is, could the disc cause problems to the pressure safety valve if they're used integrated together as you showed in the presentation?
Right, Scott. Yes. Provided the disc is correctly selected and specified, the disc should not offer any problem to the valve. It will protect the valve until an overpressure situation develops. It is critical to specify a non-fragmenting type disc for these applications. A fragmenting type disc could result in the valve being damaged or even worse, blocked. Next question there.
Okay, good. So the next question is, can rupture discs be used as a vacuum breaker?
Scott, thanks for that one. Rick again. We've got another nice quick answer to that one. The answer is yes. Again, discs are reacting to pressure differential. So if we rate the disc suitably and fit it inverted, then it can act as a vacuum breaker just as well as it can relieve positive pressure. And we talked about discs in the millibar range. Well, we can do exactly that with that very low pressure disc. So if we have a very fragile vessel that's not really capable of withstanding significant vacuum, it's a great application for that disk. What we can also do is we can engineer disks to open for positive and vacuum pressure. So that's a single disk that's reactive to positive and vacuum pressure. They're quite specialised. They need some particular engineering to work, but they're a nice solution for example, for tank protection, very widely used in that.
All right, very good, thanks. So the next question is, when a combination installation of a rupture disk plus a pressure safety valve is being tested in situ, is there a risk of damaging or reverse fatiguing the rupture disk when the safety valve is being pressurized during the test?
That's a good question, Scott. The disk will not be damaged provided the correct disk model is specified. A forward-acting disk design will not sustain reverse pressures close to the disk rated burst pressure. Most reverse buckling disks can tolerate reverse pressures at or above their rated pressure, so they are the best choice for this type of application.
Do we have any more, Scott?
Let's go. Yeah, we got a couple more here, so we're going to try to squeeze them in. We still have a couple more minutes left. So the next question is, I've been told that I can still install a damaged forward-acting rupture disk. Is this true?
Well, Scott, thanks. Rick again. The answer's no. We'd never recommend installing a disk with any kind of damage, and that's the disk or the holder. The disk might open low, prematurely, not open correctly, or it might leak. So that's quite a list of issues. It's not economic to put that disk in place if we think of the potential downtime if you have an issue down the line or even immediately. But most importantly, it's not safe. The disk is going in there to do a job. It's an instrument. It's calibrated. Any damage is going to affect how the disk operates. Now, we appreciate that you really don't want to be throwing the part away. What I'll say is all manufacturers will be pleased to give practical advice in that situation and support if you have any kind of issue with the disks. So if in doubt, pick up the phone, get in touch. We're here to help you.
Mm-hmm. Yeah, that sounds like a good idea. So let's go to the next one. What is a fragmenting design in a rupture disk?
A fragmenting design disk is where parts of the disk will separate on burst. Where fragmentation of the disk is acceptable, this allows for more economic designs of disk to be offered, thus reducing the disk unit cost. Non-fragmenting disks are also available. These designs are more expensive as they are harder to manufacture. These are also available in most sizes and pressures.
Thanks, Pete.
All right.
Getting to the end of the long hour, eh, sir?
Yeah. So we'll try to squeeze in a couple
us,
more quick ones here. What does it mean when a disk, to say a disk is fail-safe?
Okay, thanks, Scott. Rick here. Good question. So a fail-safe disk is designed to burst at its rating or even lower if there's some kind of issue with the installation. So what kind of issues could those be? Well, it might be damage to the disk. It might be the disk fitted with the incorrect orientation, so somebody fits it upside down, that kind of scenario. And in those scenarios, a fail-safe disk will burst low. Not all disks are fail-safe. For example, reverse-acting disks or disks with vacuum supports. It would be nice to design every disk to be fail-safe, but it can't be squared with the demands of the applications and how the disks need to be engineered to fulfill those. So not all disks are fail-safe. That's why it's essential. Anyone installing disks needs to understand the importance of correct installation, and most makers offer help and training for plant personnel if you need it.
Great. We have a couple quick ones we're going to try to get to before we wrap it up here. So next one is, what's an economic order quantity for rupture disks?
Scott, this is a very common question. There are high overhead costs in producing rupture discs. This is because the vast majority are custom made. Also, the disc manufacturer has to make extra discs in the manufactured lot to carry out destructive testing to qualify that lot. Ordering a single disc means that those overhead costs cannot be spread over the multiple discs. Generally, 3 discs is the lowest economical number to purchase, with further price reductions for larger quantities.
Time for one more, Scott?
Yeah, we got one more here. We'll go with what temperature should be used to identify the specified burst temperature?
Scott, Rick again. Similar to the earlier question, the burst temperature should be what we call the coincident temperature that the disk will see on burst. So what temperature do we anticipate when the disk is actually required to burst? And again, that's to account for the fact that in general, disks will open at lower pressures at higher temperatures than the actual rating. Again, we're back to the material properties of the disk, material becoming weaker at the higher temperatures. And what we're asking is the process engineer to analyse what's happening in the process, what's the likely burst scenario, and if in doubt, at the end of it all, then go for the lower temperature rating, because we know then if the disk sees that higher temperature, it's going to burst low, and we're staying safe. Thanks, Scott.
Great. All right, thanks. We've come to the end of the hour here, so we're going to wrap this up. Just as a reminder before we go, if you would like to view the program again, the entire webcast will be archived at www.chemengonline.com/webcasts, and it will also be found, can also be found at www.zookdisc.com. So either place you can find the program again if you want to see it. So at this point, I'd just like to thank the speakers again for the presentation. Thank you to ZOOK for sponsoring the program, and to all the attendees, thank you for spending the hour with us. We hope you enjoy the rest of the day. Thanks.